welcome you to today's IWCS webinar series event. My name is Dave Cadu, and I am your CEO and Director of IWCS. Again, very pleased to have come out of the COVID years to a successful event in Providence a few weeks ago. And this webinar series events chooses some of the best technical presentations that we had in Providence, and we have a really good one for you today to start off our technical paper webinar series events. So a few housekeeping items before we get started. Please note that as an attendee, you are part of a larger audience. During the presentation, all participants will remain in listen-only mode. And also as a reminder, this event is being recorded for rebroadcast. We encourage you to submit written questions at any time during the presentation using the chat panel on the right of your screen. So just select chat in the menu and enter your questions. After typing your questions in the space at the bottom, hit the send button, and your questions will be addressed, time permitting, at the end of the presentation. Our IWCS webinar series event is hosted by our Cable and Connectivity Industry Forum, as I mentioned. Today, we welcome Zach Eckel, Senior Business Development Engineer of Arkema in Pennsylvania, USA. Zach will be presenting his paper on PEKK, a high-performance thermoplastic for wire insulation. Again, an advanced and novel material coming into our industry. Zach Eckel is a Senior Business Development Engineer for Arkema's high-performance polymers business unit. He has over 15 years experience in the development and commercialization of materials and processes spanning various industries, including aerospace, defense, automotive, semiconductor, and additive manufacturing. He holds a Bachelor of Science degree in Chemical Engineering from Northeastern University, a Master of Science in Chemical Engineering from the University of Southern California, and a MBA from the University of California, Los Angeles. So with that, we thank Zach for being with us today, and take it on.
Thank you very much, Dave. I really appreciate it, and a big thank you to the IWCS team for inviting me to come and speak again in front of our group here. I do have my slides up. Can you just give me a thumbs up, Dave, if you can see them okay? Or just an okay?
Yes, right. Everything looks good. Yep.
Beautiful. Thank you very much. So as Dave said, everyone, thank you very much for joining us today. I spoke about this a couple months ago, and it was really great to get back in person in front of people at the trade show a couple months ago here. And so I'll speak to you about our PEKK material, high performance thermoplastic for wire and insulation. Just a brief kind of high level overview of who Arkema is. Sorry, is there an audio issue, Dave?
No, carry on. Everything's fine.
Okay, thank you. So I'll speak high level as to Arkema as a company. Some of you may have heard of us. Some of you may use many of our great polymers out there already, and I'll speak to some of that. But as a whole, Arkema is a French chemical company. We are headquartered in near Paris. We are nearly a $10 billion company. 20,000 employees across the globe, including Europe, Asia, and North America. Presence in 55 countries, and also 39 manufacturing production plants here in the U.S. And I do want to emphasize that our PEKK material is actually manufactured here in the U.S. Down in Mobile, Alabama. So when we think about all these supply chain issues and things that may be existing, you've got a secure domestic supply of this high performance polymer. We are a tech-driven company, so nearly 3% of our sales do go into R&D and development of materials and applications for them. The R&D areas do cover everything from our adhesive solutions, coating solutions, and then where I sit in our advanced materials and high performance polymers. So as a whole, we are a tech-driven company with broad reach across the globe. If you'd like, you can follow that QR code to learn more about Arkema. So I am part of the high performance polymers division, and this is essentially our portfolio here. We span the range of elastomeric materials to crystalline, amorphous, and semi-crystalline polymers. Kynar PVDF is very common in this industry. I'm sure many of you have heard of that. It's an excellent material for environmental resistance, UV resistance, flame retardancy, as well as processability, durability, and strength. Real sand is our polyamide 11, which is 100% bio-derived, inherently bio-derived, and so that's an engineering grade material derived from actually castor bean oil, which is really interesting. Incredibly lightweight, tough, and also has great chemical resistance. Similar to that, we have our PEKK, which is polyether block amide. It's a thermoplastic elastomer, everything from shoes to medical devices. It's light, tough, and has great energy return when we think about elastomeric material. But my focus today is going to be on PEKK, or what we call capstan, and this is what we call our ultra performance, right? So it sits here at the top of the pyramid of kind of end use applications for polymers. So this is when you have high temperature requirements plus high strength requirements plus chemical resistance requirements, high wear requirements or toological performance. That's where a material like PEKK will come in as an ideal solution. So all around, this is it's an excellent polymer for a number of reasons. And as I said, I'll kind of walk around this circle a little bit. High temperature performance, so the continuous use temperatures in the order of 260 degrees C, upwards of 300 degrees C for transient use. It's high stiffness, 3.9 or so GPa in stiffness, high strength, great wear properties for things like powder coating or wire coating when you're worried about abrasion resistance. It's inherently FST compatible. This is a material that's used in aerospace and defense, which obviously has very high restrictions on flammability. So in terms of heat release, toxicity, and smoke, as well as V0 burn data. Excellent chemical resistance, inert to most chemicals, everything except for maybe fuming sulfuric acid, right? So everything from solvents, bases, and general acids. I'll talk about the electrolyte properties, the dielectric constant for this material at both room temperature and high temperature. Performs exceptionally well in that space. Excellent barrier to various gases, whether it's a hydrogen sulfide or carbon dioxide. And then finally, one of the keys to our material is the fact that we have tunable crystallinity. And I'll talk about kind of the PAEK materials as a whole and where PEKK fits into that, and how we have this tunable crystallinity. And what that tunable crystallinity does is brings us into the world of having a variety of processing options where we can control the melt temperature as well as the crystallization rate. Okay. So as far as wire coating, this is going to be a high performance wire coating. If you need, again, all this combination of properties in one jacket for your material, right? So that's high temperature resistance, overall high performance, the high dielectric constant at temperature. You have an aggressive environment, temperature plus wear plus chemicals, and then it's compatible with extruding coating processes, and so it's processable on a variety of different existing lines for your application. And so some of the spaces that we're looking and we're exploring, which could be of use, right? That's going to be oil and gas, electric submersible pumps, downhole application where these environments are hot and aggressive, or even the coming applications in e-mobility or electric vehicles where magnet wire for the next generation of electric motors, where we're trying to densify motors, get higher voltages through them, higher temperature requirements, plus compatibility with whatever lubricants and things might be in these motors. So I spoke high level as to what PEKK is as a material. Now I'll scare everybody with a little bit of organic chemistry, right? Very high level. I don't know last time you had to look at a molecular structure of a polymer, but here you go. So what is PEKK? PEKK falls into a class of polymers called polyaryletherketones. And what that refers to is essentially just the backbone of the polymer. What comprises this material? You have an aryl group, you have an ether linkage, and then you have a ketone linkage, right? And in the PAEK family, what you do is you can alter the ratio of these and the structure of these to get a variety of different properties. And in the case of PEKK, what we're saying essentially is poly-ether-ketone-ketone. And so you have an ether linkage between your aryl ring and then two ketones. Now, in the case of PEKK, this is going to give you, by having two ketones and one ether, you're going to have a higher glass transition temperature, higher strength, and a higher melt temperature. Now, one of the other knob that we have, which is unique to PEKK, is the ability to tailor. It's a simple thing, but it's an important thing, which is the location of this ketone on the aryl ring, right? So you have your meta and your power position, or what we call terephthalic or isophthalic structures. By creating essentially a copolymer, more or less of itself, we can tune the crystallization kinetics or the chemistry and the final properties of this material to be applicable to a variety of processing conditions, and also tune the end properties. And so what we do is we create a ratio or a copolymer of these two, and the 8000 series would be an 80-20 of the T to I, so the T being the higher percentage. The 7000 would be a 70-30 ratio, and then the 6000, excuse me, is going to be a 60-40 ratio. So as you approach kind of a more 1-to-1 ratio, what you'll actually do is lower the crystallization rate and also lower the melt temperature. And so this will open up a window of processing which isn't achievable with some of the other PAEK materials, especially with such a high ketone content. Now, things that will stay the same across the grades is going to be the glass transition temperature. There's a few degrees difference between the two, and I'll show this in numbers on the next slide. The fire resistance is going to be the same, the flammability, because this is essentially the same molecule, same polymer. And then also by adding another ketone, we actually have a higher polarity, but that's going to be uniform again across the different series of PKKs. But that higher polarity will later translate into some different properties for us, which will include metal adhesion. And I'll show a slide on that. Okay, and so, where does PEKK sit versus some other PAEK materials? And I'm just going to talk high level about the temperature profile, really. And so, because we have a higher ketone content, we're going to, in general, have a higher glass transition temperature. So in our 8000 series, we're looking at about 165 degrees Celsius. And the 6000, again, it's only a few degrees different, but 160 degrees Celsius. And this will, of course, drive the mechanical properties, the temperature at which you can operate the material. But you also see that translates itself into electrical properties as well in dielectric constant. And I'll show that in another slide. Of these materials, of the PAEKs, becomes, an alphabet soup of E's and K's, but you've got PEKK, which is very common, and I'm sure many of you have seen that material before. And then we've got PEK, which is ether ketone, and then you've got EK, EKK, right? So again, just flip-flop depending on how many ketones and things are in these. And what you'll see as you have more Ks, the melt temperature will go up and the glass transition temperature will go up. But in the case of PEKK, our material, you have the ability to tune that and retain a lower melt temperature, but still keep the higher TG. And so that's one of the big differences here for us. Right? And in the case if we're thinking about wire coating, depending on how you're doing your coating, all these grades are adjustable for you, whether it's powder coating or extrusion, and depending for the end application. Now, an area I mentioned previously is the crystallinity kinetics. And so by, again, increasing the T to I ratio, or normalizing it to closer to a 60-40, you can actually slow the crystallization kinetics down so that you can retain an amorphous polymer, or you can do a controlled crystallization or controlled anneal. And so what you're looking at here is essentially the half-life crystallization time versus the temperature. And we've also called out the TG of PEKK material and the TG of our PEKK. And the red line is going to be PEKK. And so at 180 degrees C or so, you're more or less going to be crystalline immediately. Now, as you get to 200 or 220 degrees C, the 7000 and 8000 series PEKK materials will behave in a similar way. These will crystallize relatively quickly. But you can see at lower temperatures there is more control to be had. Now in our 6000 series, you can see it's much slower crystallization, and to get a high level of crystallization, you really wind up having to do a 240 degrees C anneal, which is really beneficial if we think about some of these thin film processes and where shrinkage or warpage may be an issue. Things like powder coating or 3D printing, especially where you have large parts that are being formed in a layer, where you have to really control the kinetics of that crystallization in order to either control the crystallization or to prevent it entirely. And the same can be true for wire coating. So in the case of an amorphous material, you're going to, of course, have some level of transparency and also a little bit more flexibility, but your overall strength and stiffness may be lower. But in the case of the semi-crystalline material, you're going to have the peak performance out of the material. So it's really what we're not prescribing which one is the right one. What we're saying is we have options for it. Now, because of this, as I mentioned, a variety of processing is available for this material, everything from extrusion all the way to powder coating, right? So everything from bulk processing to thin film processing. Now, I won't spend much time on any of these today, just because, we're just going to be talking about a wire and things like that and the material as a whole, but certainly we could do deep dive on some of the different applications. But the beauty that I want to point out about PEKK is the ability to control the crystallization and the melt temperature, which allows us to address a variety of these different processes with this material. Okay, so I'll start to dive into just some specific properties about PEKK, and the last ones I'll kind of touch on will be the electrical, so you'll have to wait for that one. But what I'll talk about here is just the mechanical performance, straight tensile properties as a whole, and what we're doing is comparing this to PEEK, very common PAEK material, which is used in a variety of applications. I'm sure, as I said earlier, I'm sure you've heard about that one. But what you've got on the left is the tensile strength. What you've got on the right is the tensile modulus. Now, the key thing here, though, is we're looking at the elevated temperature performance of these materials, okay? So both of these charts will go from 130 to 170 degrees C. And what you can see, due to the extra ketone in the polymer and that higher TG, what we're seeing is a higher tensile strength at temperatures. So at temperatures of 150 to 160, 130 to 160 degrees C, you're seeing a higher tensile strength for the PEKK material. So for these extreme applications that we're talking about, you're going to have a higher strength. And the same thing is going to be true for the tensile modulus, yes. At about the 160 mark or so, you're going to see, the peak is dropping, while the PEKK is going to retain its modulus for a longer duration at those temperatures, for a higher temperature. So again, because of that high temperature performance, high temperature properties of the material, we're going to retain these properties. So the same thing is going to be true for creep resistance. This is creep resistance of, again, we're comparing injection molded PEEK to PEKK. This is our 8001 series, so this is going to be the one that has the higher ratio of T, so higher crystallinity, or faster crystallization, excuse me. But we've got PEEK and we've got PEKK at both 135 degrees C and 50 MPa, and then 150 degrees C and 35 MPa. And what you're going to see is the same trend here, is going to be, for PEEK, you're going to see, an increase in the elongation or strain on the order of minutes, whereas for injection molding, it's going to push it out further to about hours. And for the stock shape, you're going to see an even longer time. So really good creep properties relative to some of these other materials in the ultra performance, high performance thermoplastic space. And the same trend is true. Of course, it's exaggerated a bit here for the 150 degrees C, but the same trend is true where we have a higher creep performance, which is consistent with our higher temperature stability versus some of the other PAEK material. Okay. This is going to be the compressive strength and modulus of PEKK. Same thing, machine stock shapes. And this is going to be against both PEKK rods or PEEK rods. And we're going to see a similar trend here, right? About a 20% or so improvement over PEEK. and that's going to be at room temperature. So this test is specifically at room temperature, machine samples out of stock shape, and which you can see for PEKK in this column here, we're going to have a modulus of about 3.9 GPa and a compressive strength of about 167 MPa. And whereas for PEEK, you're going to see about a modulus of 3.2 and a strength of about 140 MPa. Next, we'll talk about the PEKK chemical resistance. And so this is going to be environmental stress cracking resistance of both amorphous and semicrystalline PEKK. And as I said, there will be a difference here, and it's important that you all understand there's going to be a difference between amorphous and semicrystalline. So what we did, a 1 week immersion at room temperature, essentially, of the semicrystalline and amorphous PEKK. And then you'll see, this is going to be a spider chart, but, 1 will be dissolved, and a 10 will be there's no effect on the material after a week of soaking. And then you'll see there's kind of a gradient in between, right, where number 4 is swelling and number 7 is going to be there's ESC after a few days. Okay. So on the left, you're going to see a comparison of the amorphous, the semicrystalline, PPSU, and PEI against some very common chemicals that are going to be in the aerospace and defense industry or the oil and gas industry, right? And so you've got just a quaternary ammonium disinfectant, ethanol, jet fuel, Skydrol, which is common hydraulic fluid, and then some aggressive solvents like toluene, MEK, and methane. And so what you can see is the brightish blue line is going to be our semicrystalline or annealed PEKK, and what you can see is essentially unaffected by all these chemicals, right? Which is fantastic. And now you can see also comparing that to PEI and PPSU. Some of the chemicals that are attacking these or essentially dissolving these materials do not affect semicrystalline PEKK, and this is at a 0.5% strength. Excuse me. So I also have it as 1.1% strength. Now, the thing to point out, as I said, is we are comparing the amorphous PEKK as well, and what you can see is the amorphous PEKK still does better than the PEI and still does better than the PPSU, but it of course will underperform the semicrystalline PEKK. Now, this is a completely expected result, and so there's no surprise, but it just shows you that depending on your processing and your application, we have the flexibility to have a material that might fit for you. Along the world, in that same realm of environmental resistance, chemical resistance, we have done NORSOK testing. And the NORSOK testing is very common in oil and gas for downhole conditions, right? And so the NORSOK exposure test, the acceptance criteria for this is a limit of plus or minus 5% on swelling. The tensile strength, elongation, and modulus cannot change by more than 50%. And there can be no visual deformation, right? So that's the characteristic of the polymer going through the test. Now, the test itself is going to be a mixture. It's going to be an exposure test of hydrocarbons, sour gas, and water, where sour gas is comprised of carbon dioxide, hydrogen sulfide, and methane. And the polymer is then exposed for 60 days at 100 bar at 3 different temperature conditions, right? So 200, 210, and 220 degrees C, right? So this is a really aggressive test, right? Where we're talking about combining a variety of different treatments or exposures, right? So you've got temperature, you've got pressure, you've got chemical, all attacking this polymer. And what we find is that PEKK does incredibly well. So this is the 220 degree C test, and this is compared against a variety of the other PAEK materials. And what you can see, we've got PEKK injection, this is extruded, injection molded, and then we're comparing to PEEK, which has also been extruded at 220 degrees C, tested at 200 degrees C, and then also PEKK, which if you remember earlier, I mentioned as a different PAEK material, and then PEK, another one of those PAEK materials. And what we see is that PEKK survives the entire life of the test, more or less unaffected, or very slight drop down in the tensile performance of the polymer. Now, and And it also exceeds the performance, as we mentioned earlier, just comparing some of the room temperature and the standard test data. It exceeds the performance of the PEEK material. PEK and EKK clearly have a sharp drop off in their performance only after about 2 weeks. So as we look about applications for extreme conditions where PEKK may be useful, clearly oil and gas downhole conditions are an area where we can survive and we can bring value to folks. Okay. I'll only talk briefly on this one. This one's a bit of an eye chart, but really what I'm just showing you here is we've done a lot of flam testing on this material. This is an improved material and does exceptionally well. Inherently, there aren't additives that are put into this material to make it an FST. PEKK as a material has these properties on its own. You can see the V0 test, the OSU, low OSU, high oxygen content, oxygen index. And then, when you burn it, you got carbon monoxide and carbon dioxide, which is expected based on the chemistry I showed you. So that's fantastic for hazardous applications. So as I said, I did promise I will show some electrical data as well. And so just reminding you, all these benefits that I've showed you previously, the mechanical performance, the chemical performance, the thermal performance, all combine into PEKK to make it a great material. And so in order to become a wire coating material, we have to know, does it actually perform well as in electrical testing? And so I'll show you both dielectric constant of the material, and I'll show you dielectric strength, and we can go from there. So what I've got here is the dielectric constant, and like some of the other data I showed you before, this is going to be both at room temperature all the way up through a hot performance. And so the black or the darker blue line is going to be our PEKK material, and this is tested at 40 hertz. We have other test data. I won't have it here today, but I do have 60 hertz, 1000 hertz, which I could show at a later date. But just to show you the PEKK material at 40 hertz as compared to the PEEK material also at 40 hertz, in which you can see, at room temperature and things, we're close. It's a little bit better, but really where you see a big difference between our materials is, again, at the elevated temperatures, right? So you can't see it that well in this chart, but there's actually a point around 150 to 180 degrees C where we actually have a lower dielectric constant. We do almost intersect here at about 190, but then once you get above 200 degrees C, again, we retain that lower dielectric constant for extended temperatures. And so hot and aggressive environments, PEKK really is a great material. And then to take that a step further with the dielectric strength. So, obviously a higher dielectric strength here being better versus a low dielectric constant being better. You all know that probably better than I do. Again, we're comparing up through elevated temperatures, the PEKK material to a common industry material. The thickness for these would be about 160 microns. And what you can see, same pattern that we've seen consistently throughout a lot of the performance data. As we approach 150, 160 degrees C, the performance of the PEKK continues to outperform the PEEK material due to the higher thermal characteristics of the PEKK. And so our dielectric strength, don't want to mess that up, our dielectric strength out up through 100 to 250 degrees C clearly is much higher than PEEK will be up at these temperatures. And so looking at that data, these are great. This is great material for high voltage applications where the voltage itself is bringing temperature, or environments where you're going to be aggressive, you're going to be hot, and there's going to be chemical attacking. So high voltage wire, magnet wire for next gen E motors, which I'll talk about a little bit, as well as busbar coatings for EVs as well, where you're going to have a lot of current running through these materials, and you're also worried about safety effects such as thermal tunnel. Okay. Briefly, I mentioned, we have this additional benefit of having a higher polarity, being a EKK, additional ketone. And so what we're just showing here is, this is just a rough test on, this is a test we did over molding PEEK versus PEKK onto a bare metal substrate. So no primer here to ensure good adhesion, just the two materials itself. Of course, a clean, properly prepared metal surface, and then what you see is about a 2x increase in PEEK, in PEKK over PEEK in the adhesion test, right? And so in the PEKK material, we're seeing interface separation, which means the polymer is peeling off of the bare metal substrate. In the case of PEKK, we are seeing interface, but we're also seeing polymer deformation and some metal deformation, which means we've really got a nice bond to that metal, and so very good bonds to the substrate. As I said, I'll talk just high level here in terms of potential applications in electric vehicles. And one of the ones we're looking at right now is thermoplastic wire insulation for magnet wire. Versus classic thermoset enamels, we've got a much lower dielectric constant, especially at temperature, as we've shown. And also, you'd be moving to an extrusion process, so you can remove some of the cost of solvent processing from the traditional enamel coating. And so this makes it, as motors are looking to densify, which is going to drive, potential voltages higher, and of course the operational temperatures higher to 180 to 220 degrees C. PEKK lends itself well as an insulation material for those magnet wires. The higher polarity is going to give you better adhesion to those wires. And then we also have this unique benefit too, in terms of a potting material. Because we have this control over the amorphous and the semicrystalline behavior of the PEKK material, we can actually get layers to bond by taking them through anneal. So if you put two amorphous pieces of PEKK together, you can get an adhesion by annealing them together as it crystallizes. This is actually something that's really been beneficial for us in the world of 3D printing or powder coating, where you're looking to build up layers to create your final part. Could be beneficial in terms of potting for electrical as well. And then again, as we mentioned, we've got the improved dielectric performance, which will drive things like PDIV and just insulation properties in general. The last thing I'll leave on, now this is very general, because this dives into the world of kind of next gen materials for us, so a bit proprietary. So I won't tell you what these are, but what I will say is that we have the ability to alloy this material. So PEKK blends well with a variety of high performance materials. And so right now we're working on two specifically. The first one is a material to push the thermal properties even hotter. And so we've been able to show an increase of about 15 to 25 degrees C, excuse me, for the TG, as well as shifting out further the rise in dielectric constant as you increase temperature, right? So dielectric constant will stay lower as you increase the temperature with this alloy we're creating. And then the second one is dropping the dielectric constant overall. It's even starting dielectric constant, as well as improving the flexibility and the mechanical performance of this material. And so that's the one I've got a little bit of data here on the right. So this is going to be alloy B. You can see, I don't have very specific numbers here. It's the kind of thing where we'd probably have to have a separate conversation one-on-one to talk a little bit more detail. But in the case of alloy B, you can see we've got a lower dielectric constant up through high temperature, right, which is fantastic. And then we also can increase the flexibility, right? So we're dropping the stiffness, decreasing the overall tensile strength, but increasing the elongation of break, right? So some more flexibility as we look at a variety of applications where wrapping or winding wires and things. All right. So that's, in summary, that's the technical side of all this. I'll just, as a product goes, PEKK is available in a variety of different formats. We make it direct as flake or like a rice type material. It's available as pellet and powders. So depending on powder coating or extrusion processes, you can fill this material. We've got glass filled, carbon filled, as well as a variety of wear grades as well. And the last piece is we do offer this in 12 grades relative to viscosity. So we've got the 6, 7, and 8,000 series, which controls the melt temperature and the crystallization kinetics. We've also got a variety of viscosity levels depending on the process conditions. And so the 6004 series will be a much higher flow rate at temperature, which is great for compatible resins. So I'll end there. I'm happy to take any questions, but please, I encourage you to reach out to me directly or connect with us on our various media channels.
Thank you very much, Zach. Very, very informative presentation for an exciting material that our industry is very interested in. we did get a number of good questions, so I'd like to present those to you and see what your response is. But also, I will be providing Zach's contact points at the end so that you can contact Zach directly if you wish. But UL temperature rating, have you identified specifically a temperature rating for this material, PEKK specifically?
So I don't know if it's UL, but I know our continuous use temperature is 260 degrees C. That is
250.
260, 500 F.
Okay. And I know some of your charts kind of started to see a degradation starting at that like 200 level, you know, for some of your dielectric properties, for example, or things like that. So so that's obviously a very high temperature material. Have you checked the dielectric transmission capabilities, for example, that's used in data cables?
That is not one that I'm aware of. We have testing on, but certainly if there's an interest, we can discuss how to get that test done if somebody has a specific application in mind. But that's not one that I apologize I didn't have handy.
Okay, and what about the behavior of PEKK at different frequencies? I know you touched on that, but
yeah, I do have a variety of different frequencies. I don't have them here today for y'all. We haven't released all of that information, but we do have a number of frequencies that we did measure for dielectric constant. So happy to connect with someone who has that question specifically, and maybe we can arrange an opportunity to share that.
Yeah. You know, considering the higher temperature capabilities and the heat mitigation, you know, obviously there's an interesting combination of flame retardant, temperature resistance, mechanical properties. Is PEKK a viable alternative insulation for powered or you know, power over Ethernet, fault managed power class 4, those kinds of applications?
I'll be honest with you, I don't know. I mean, I don't know that application well enough to say specifically. What I can say is if looking at the performance and properties of PEKK, if you find that those conditions begin to overlap with the needs that you have or the environment that you're exposed to, it's certainly worth an exploration of the material. You know, we're processable in a variety of different ways. We've got a variety of great mechanical, chemical, thermal properties, and clearly dielectric properties. And so I would suggest a benchmark against what you're using today, and then a conversation about, you know, how PEKK might be beneficial in that space. Yeah, I do apologize, not being an expert in each of these fields, I can't speak directly to that.
And before I do the rest of the questions, I do want to remind folks that if you have a question for Zach, please enter it in the chat function, and then we'll address your questions as time permits to Zach. How flexible is PEKK for smaller cable applications, for example, 18 to 24 gauge?
Yeah, absolutely. It's a great question. So the beauty is it depends on if it's amorphous or semicrystalline, right? So as a semicrystalline material, you're going to see about 30% elongation, 15 to 30% elongation, depending on the level of crystallinity and the grade that you use. And so there's your first limit. Now, if your application can use an amorphous material, that can go up over 80% elongation of failure, right? And so if we're thinking about you have a tight winding, you have tight gauge wire, using it, but your chemical or your thermal environment may not be as aggressive. Certainly PEKK as an amorphous material could be useful for you in that case. And we are looking at applications where that is beneficial over the fully annealed material.
What's the difference in comparative tracking index for PEKK versus PEEK? You know, just for a comparison.
Yeah, that's a great question, and that's actually this is not the first time I've got that. We haven't done that data yet. But it is in the queue to do because it is one that comes up quite often. When folks ask, you know, in general, as a good starting point, if peak is a value of X, we're going to be in that range. And the same thing is true if we haven't tested all the chemicals out there to be resistant against. The first benchmark we say it's a PAEK material. It's going to be similar in performance at a starting point to peak. And so we can go from there though. yeah, so I don't have the exact data, but that's where I'd point you to as a starting place.
Very good. And I think this was consistent with a few of the other questions, but do you have dielectric constant information on 1 gigahertz to 2 gigahertz and higher?
You know, that's a great question. I have to see how high the data I have goes. We might. I don't know if we have it over 1 gigahertz, but I might have some high stuff. I'll have to take a look. I encourage you to reach out and schedule that conversation with me, though, and we can potentially get you an answer.
I think that's consistent with the inspiration that your presentation has for a number of new applications. Is there any parameter for PEEK that's better than PEKK?
Yeah, that's another good question. I mean, we'd start to get into nuances. You know, overall, I think we both do different things very well. I apologize. I don't know if there's anything that they really excel at us versus, you know, can't speak to that. I don't know the full gamut of the peak performance. I know there's a lot of grades out there.
Right. Are you aware of any ASTM or IEC test methods that you use to test adhesion? Do you have any, you know, quantitative values that were achieved?
For adhesion to, I showed the overmolding test that we did. I believe that was an ISO standard we tested to. I could look that up. I don't want you guys to have to watch me look at my screen. There is an ISO standard that we tested that to, and I could share that information offline.
You can share that offline. Okay, good.
Yeah.
Can you cross-link PEKK?
I believe you can. We haven't done much of it ourselves, but I believe it is possible. Yeah. It's not been a focus for us.
Right. And how would you compare the manufacturing process of PEKK as it, you know, compares to PEEK? Is it any different?
I can certainly say that it's different. I'm not allowed to discuss the details of our chemical synthesis or production process in a forum like this. I apologize for that. I can just tell you that it is different.
I think it's probably more about the product processing. You know, what type of extrusion would you say is suitable for PEKK versus normal type of extruders, those kinds of things?
Yeah, certainly. No, that we can speak to. You know, and I'll preface by saying that I'm more on the application side and less on the actual processing side. Overall, you're going to have, you know, a range of melt processing temperatures, but it's going to process in a similar way. You just have to accommodate, and we have a tech service team dedicated to helping folks do this in their facilities. Also, lots of literature to help with that too. But you know, you have to accommodate the fact that this is going to be a higher melt temperature material. It's going to be a harder material, and it's going to be a higher TG. So, you know, as long as your extruder and your systems can manage that, it'll be compatible.
Okay. For EV applications on battery connections, which series is being tested?
I'm sorry, I don't understand. I don't know that answer to that question. Which series is being tested?
Yeah, that was the question. I assume it's, you know, a different type of material or a different formulation for these.
Which PEKK series? I'm sorry, I thought you were referring to if there's a series of bus bars or connections. If it's going to be, yeah. So if it's going to be, there's a couple different ways we can do that. It's pretty interesting. You can powder coat them actually, and in that case, it'll be of our 6000 series. If you're going to extrude them, though, it'd likely be either the 7000 or the 8000 series material. We actually have a person dedicated to bus bars and happy to connect with him. He's the expert in that space, and we could talk about that more. But it's certainly a really interesting application because you've got high voltages, high operational temperature, but you've also got the risk of, you know, catastrophic events or battery shorting where you need to maintain insulation if these things go up past 1000 degrees C, right? And we've actually we're exploring the ability to do that, but inherently we believe that it can because of the FST properties and because of the nature of the materials.
Right. And I trust you'll be, you know, sharing with the industry updates and improvements that are ongoing, you know, that, you know, for the 6000 series or other blends.
Absolutely. We love to communicate. We love to share the information we've got on our material. it's our goal is to help everybody here design better products, better materials, better processes with great materials. So appreciate that.
Yeah, just a couple more questions.
Sure.
Is PEKK suitable for jacketing as well as insulation?
Again, I mean, I think it's all very application specific. What you're after. If you're just looking for, making your jacket chemical resistant, or excuse me, your wire bundle chemical resistant, certainly that's an option. It just becomes compatibility to the other materials that you're going to extrude on. This is going to be a hot temperature extruded material, and so can everything handle that and be processed with that?
Yeah, and the final question, what about resistances, environmental resistances to oils, mud, those kinds of things, and in combination, the flame retardancy and flammability ratings. So any kind of environmental commentary?
Yeah, so just to be clear, this is so in terms of mud and oil and all those things, like I said, we're resistant to all those things. Really, the only thing that can become problematic for us will be extremely concentrated acids, such as sulfuric acid, 100% sulfuric acid, or 98%, whatever fuming is. And then also, direct UV exposure can be problematic too for these PAEK materials in general. So in terms of oils and muds and things like that, I don't see an issue there. Now, if you're asking the specific FST performance when exposed to those things, I don't necessarily have that information. I don't have, something that's been soaked in toluene and then run through FST. I don't have that information. Certainly, we could discuss if that was important for someone.
Excellent. All right. Well, listen, a lot of great questions. We thank the audience for entering those questions, and certainly a very interesting and inspirational presentation by Zach. So again, thank you, Zach, for this very interesting and important topic today. On your screen now, you'll see some contact points. Should you wish to contact Zach after today's event directly to get some offline discussion going. Each of these IWCS webinar series presentation events are recorded and will be archived on the IWCS website. That's iwcs.org. It normally takes up to 2 weeks to have these posted. We are in the process of updating our website coming out of the conference, so please be patient with us, but you'll be able to revisit this presentation again. The IWCS webinar series will conduct technical paper presentation webinars and sponsored company events several times each month. Our next scheduled technical paper presentation event will be on Friday, December 16th at 10:30 a.m. Eastern USA time. Each of you will be receiving an announcement for the event, and please feel free to share our announcements with your colleagues so that they can join in and register as well. I think we've reached our time limit, so again, I want to thank Zach, but also is important that we recognize and thank our IWCS partner sponsors who contribute greatly to the success of our Cable and Connectivity Industry Forum. Without their strong leadership and generosity, we would not be able to bring these important technical innovations and information to you and our global community. Again, thank you to these leading suppliers in our industry for your support. For over 71 years now, the IWCS Cable and Connectivity Industry Forum has been the recognized leader in showcasing new technologies and cable and connectivity products, processes, and applications. Our next 72nd annual Cable and Connectivity Industry Forum will now take place live on Sunday through Wednesday, September 17th through the 20th, 2023, at the Gaylord Palms Resort and Convention Center in Orlando, Florida, USA. So please watch your inbox, social media, and our website to learn more as this exciting information becomes available. And of course, please visit our website at iwcs.org for more event details. So again, I can't believe we're already here, but happy holidays for those of you in the USA. Happy Thanksgiving next week, and thank you for participating. And this concludes today's webinar event. Have a great weekend, everyone.
Thank you, Dave. Thank you, IWCS. Thank you, everybody on the call.
Thank you, Zach.